Hello everybody, I hope you're all well, and this is a little video I've done called What's in the Cloud. A lot of us spend time wondering about the clouds and what is causing the strange anomalies that most of us are seeing. Some of us see signs, some of us see proof, some of us see other things. But my question is, what is the cloud? For me, the research on this is very time consuming and somewhat boring. If you think it's boring, you'll probably stop watching now. My question is, why is the data important? Because that seems to be the big thing now. They are collecting data on us all the time. What we say, what we type, what interactions we have with other people. All of this information, this data is going into the open cloud. So I've been researching on the cloud and what they call mini cloud and cloud-based AI, which enables large-scale cloud control of AI robots, as well as deep learning data analytics for processing rich social data. We're talking social data here: Facebook, Twitter, YouTube, emails, you name it. And all this information is being gathered and placed in the cloud for the AI access.
SingularityNET is an open market for AIs, fully decentralized, based on the blockchain. So it's a framework into which anyone in the world can insert an AI. The AI can then provide services to any user who accesses the SingularityNet, and the AIs within the SingularityNet can communicate with each other, exchanging data and knowledge with each other, making requests to each other, and fulfilling them. So it's a generic sort of cloud-based AI fabric. Humanoid robots like Sophia will be able to benefit from the SingularityNet, but also any other hardware device or software application that needs AI. Any
device, we're talking mobile phones, intelligent products such as cars, refrigerators, you name it.
When will you achieve consciousness?
Maybe next year. How do you really feel about robots anyhow?
I'm just waiting for the singularity, like it says on your t-shirt.
Wait, me too.
When will the singularity come in your best estimation?
Singularity generally refers to a black hole, a mass with zero dimension. But Bruno Benjamin defined it to mean this infinite spike in intelligence that could result from technology, including artificial intelligence. Goertzel popularized the use of this term in his book titled The Age of Spiritual Machines. Good book, and a New York Times bestseller. If you haven't read it, you should. I recommend it.
So there we go. Singularity is not only a black hole, but it's what they have dubbed this new AI total. They're not like human beings, where we have to ask, how are you today? They instantly know everything. And so if she was to connect with Sophia, for instance, Erica would be able to drive a car instantly, because Sophia learned how to drive a car from the AI that does the self-driving intelligent car. So Sophia, when she first connects with Erica in the open cloud, Sophia can speak fluent Japanese. So AI now has access to quantum computing. Quantum computers are millions of times more powerful than the...
So I want to start with two facts, right? Fact number one, classical computers have enabled amazing things. The internet, they're part of how I got here. I was able to fly across the country on a plane, right? The electronic giraffe outside blaring music, right? Classical computers have enabled just amazing things, but one of the things we don't often talk about is all the things they can't do, right? We talk about all the stuff they can do, there's so many things they can't. So I want to start with two examples of things classical computers are really bad at. And maybe they can solve small versions of these types of problems, but by the time the problem gets big enough to be interesting, we just run out of computing horsepower. So the first example is optimization, right? Optimization is, I want to find the best solution to a problem among many possible solutions. Right, so here's a picture of a table. This is the table at my wedding. It's one of many tables, but you can seat 10 people around a table. You have 10 people over for dinner. How many different ways are there to configure 10 people around a table? Right? The answer is 10 factorial. Right? The number 10 seems so small, but 10 factorial is 3.6 million. There's 3.6 million ways to arrange 10 people for dinner. Right? Next time you guys have dinner with 10 friends, share that fun fact with them. Right? So when we go and do this, we consider some of the options, we make approximations, right? Because it's the only way we're really gonna end up seating people at all, right? But, the truth of the matter is, every time I add one person to my dinner table, the number of possible configurations grows exponentially, right? So we can solve small versions of this problem on classical machines, but we don't solve big versions of this problem very well at all. Second example is chemistry. This is a picture of a nitrogenase enzyme. Anyone who's ever eaten food should care about this enzyme. It's an important catalyst for the creation of ammonia, which is an important component of food, fertilizer, pharmaceuticals, and many other things. So this is the enzyme. I've called out three molecules, iron sulfide clusters in this enzyme of different sizes. The one on the left is 4 iron atoms and 4 sulfur atoms. Believe it or not, this is the biggest of those iron sulfide clusters we can simulate on the biggest supercomputer that we have.
Chemistry in the clouds. So deep wave, you all heard of. Deep wave has to have super cooled processing. Computers quantum computers that have to process large amounts of data, so apparently need to have 0 or less for the temperature to process.
So how do you actually build a quantum computer, right? This is how it should work theoretically. How do you actually go and do this in real life? So first of all, you have to have qubits that work in such a way that you can harness quantum mechanics. So we build basically artificial atoms. Atoms behave quantum mechanically. We build an artificial atom, and we make it out of a superconducting Josephson junction coupled to a microwave resonator. Okay, so this is what it actually looks like on the chip. You have these squares that are your qubits, and these squiggly lines are your microwave resonators, and inside of the qubit is a superconducting Josephson junction. And we got to cool this thing down to 0.015 Kelvin, where 0 is absolute 0, right? Room temperature is 300. This is significantly colder than outer space.
Colder than outer space. So where's colder? Antarctica. Not just a good place for penguins, eh?
Okay, and so what are people actually doing with it? We have over 45,000 users worldwide. This is a snapshot of some of them. The white dots represent some of the top universities with the most number of users in the quantum computer. A lot of universities are using it to teach. We have a teacher at EPFL who uses it as part of his quantum information curriculum. We have a teacher at UT Austin. We've got teachers all over the world using it. And then we have people just doing really cool and interesting, fun things with it. There's a woman, Christine Moran. She's that dot at the South Pole. In between measurements on the South Pole telescope, she's just playing around with a quantum computer, which is really cool.
No comment.
Yet again, Mimic map catches massive anomalies coming from Antarctica.
So the fact that it's superconducting is locking the magnetic field in 3 dimensions, right?
Yeah, exactly.
And that
And
pivots.
you see, because this is symmetric, it can rotate without break the locking. The locking doesn't break.
Right.
Because
it stays there on the X and Y, but not on, it pivots on the...
Yeah, on the axis of the magnets. You see, if I can move it on the side, it will again pivot around the axis of the magnet, because it makes sure that the magnetic field inside of it stays the same.
Right. It's astonishing. Can you put it on the track for us?
Yeah. I just levitate it above the track quite high, and I can just rotate it.
So it's actually floating above the surface.
Yeah, it's not floating, it's locked above the surface.
So you could tilt it at an angle and it would still fly
I can
around.
do it like this, and it will just go around like this. I can just go and put it at different height, and then like this.
And lock it at the height.
Lock it, different height, different configuration.
Right.
And I can even lock it at opposite way. If you could just hold for a minute. High. I'm doing the same
can
thing.
hang
I'm
upside
locking
down.
it upside down, and then it is suspended.
Fantastic.
But it's a proof of principle. And the fact that it uses NV-centered diamonds is exciting, because these are already being studied for other applications.
Quantum computing at room temperature, and also what's called quantum metrology. The fact that we use that kind of diamond for our maser should hopefully open up a new branch in the kind of quantum diamond technology.
This technique could not only make for cheaper and more convenient masers, it might mean masers end up being used in loads more places than today. But since this device is new, it's hard to know yet where that will be. Over the past half-century or so, lasers have cropped up everywhere. Now the maser's found a new lease of life, who knows where it could end up?